Hi everyone, welcome back to the webinar. Very happy to have Pavlos Motakis from York, and he's speaking on separable space of continuous functions as Calkin algebras. Pavlos?
Thank you, Bunyamin. So a couple of things to say before I start. So first thing I wanted to remind everyone is to contact Bunyamin to arrange for dates to give lectures, to fill up the schedule again as it used to be. Only because we're coming out of COVID, hopefully coming out of COVID does mean that we should not keep doing this. Second thing, I already gave this lecture in August at a session at IWOTA arranged by Kevin, Tomek, and Niels. So it's largely the same lecture. I restructured it a tiny bit. I took out a few things. I added more things because this is a longer talk. So I hope I have time to talk a bit about the details at the end. Third thing, so this topic of Kalkin algebras is one I've worked on in the past. I have a couple of papers on this, but that was a few years ago, and I was reminded by it by some questions asked by Chris Phillips during Valentin Ferentz's talk at the seminar back in April. Then the last thing I want to say is that I finished writing this paper, so it's written. So a preprint will be available soon. I'm just waxing it up a bit so that it's a bit more presentable. Okay. So let's start. So it's organized as follows. It's 4 sections of very unequal length. So we'll start with a bit of background. What are Calkin algebras? What have they been used for? Then we'll talk a little bit about explicit Calkin algebras. For example, space of continuous functions Calkin algebras. So we'll make the question more precise, some known examples, just very briefly. And then the third one is very important, the relation between general quotients of L of X. Calkin algebras are a specific type of quotient of L of X. We'll talk a bit about general quotients of L of X and how they relate to tight control of operators on a Banach space X. From the viewpoint of this lecture, Calkin algebras are not a purely algebraic object. They are a very analytic object. They have to do with the structure of bounded linear operators from the Banach space X. And this also relates this topic to modern Banach space theory. And at the end, I want to give you a bit about the proof, so a very bird's eye view of a construction of a space. And I want to try to give you all the important ideas without any of the technical details. And since I wrote the paper, now I know how to do this better. And since I have more time, I hope I will be able to give you some of these ideas. Okay, so let's start with a background. So given a Banach space X, we denote by L of X the space of bounded linear operators. And an ideal is going to be a closed subspace. So we're talking about closed ideals, call it A, that is both a left ideal and a right ideal. So if you multiply things from the ideal with anything from the left or from anything on the right, it goes into the ideal. So when I say ideal, I always mean closed left and right ideal. So some examples. There is K of X, the space of compact operators on a Banach space. So an operator T is compact if whenever you take the unit ball and you take the closure of its image, then it's a compact subset of X. Then similarly, instead of saying compact, you can change compact to weakly compact, and this gives you the ideal of weakly compact operators. And particularly important to this lecture also is the ideal of the strictly singular operators. So an operator is called strictly singular. If you don't remember, let me remind you, means that for any subspace of the domain that is infinite dimensional, if I restrict the operator on the subspace, then this is not an isomorphic embedding. So not only is T not an isomorphism, so this would be the singular, it is not an isomorphic embedding, not even that, and never is its restriction in infinite dimensional subspace an embedding either. So then we say it's strictly singular. So remark is that if you start with an ideal in L of X and then you take this Banach space quotient, this is of course a Banach space, but it is also a Banach algebra. And what you do is you take an operator T in L of X, and you can map this to its equivalence class in this quotient, and then you can equip the space of equivalent classes with a multiplication. And this is then well defined, this natural multiplication, because the denominator in your quotient is an ideal, and this makes the Banach algebra. And the specific algebra we're talking about mostly today is the Calkin algebra, which is the quotient that has a denominator the compact operators, this particular natural ideal. And just a small remark before we talk a little bit about the Kalkin algebra and what it's been used for is that if you take an infinite dimensional Banach space, then this is a non-trivial quotient, because if you take the identity operator, then this is not a compact operator, so it is not going to be mapped to 0, it's going to be mapped to an identity element inside the Calkin algebra. But if your space is finite dimensional, then every operator is compact, so you just get a trivial quotient. So what has the Calkin algebra been used for in the past? So the first way it was used is to classify ideals. Starting with a Banach space, classify ideals in the space of operators. So in 1941 is when Calkin first defined this object for little L2, so that he took the quotient, all the operators in L2 over the compact operators in L2, and he proved this has no non-trivial ideals. And he was able to deduce that therefore the compact operators is only non-trivial ideal in this space. So there's the zero ideal, there's a compact operator, and then there's a whole space, and there's nothing else in between. And in general, if X has a mildly nice property, the approximation property, then if you know the ideals in the Calkin algebra, you can use this to classify the ideals in the space of bounded linear operators. So under some mild assumption, if you know the ideals in the Calkin algebra, then you know all the ideals in L of X. And this is a very, very simple almost bijection between the ideals of these two spaces, but I don't want to get into this right now. So another way that the Calkin algebra has been used is to characterize Fredholm operators on any Banach space. So if you start with an operator on a Banach space X, then it's going to be Fredholm if and only if its image in the Calkin algebra is invertible. So if you want to remember what a Fredholm operator is, it means that it's an isomorphism between subspaces of finite codimension. So you take a subspace of finite codimension in X, and if it maps it to a subspace of finite codimension isomorphically, then this is a Fredholm operator. And then there is some other noise going around in the remainder that we don't care about. Okay, so this is how it has been used classically. So let's talk a little bit about Calkin algebras in the context of this this lecture today. So the very, very natural question is, start with a unital Banach algebra, call it curly B. Does there exist a Banach space X so that B is isomorphic to the Calkin algebra of X? And when I write here or say isomorphic, what I mean is isomorphic as a Banach algebra. So this means that there exists a homomorphic isomorphism. So we want to preserve the Banach algebra structure as well. So this is a very rudimentary question. The first time I've seen it written was in Taubert's paper. In 2012, actually in his thesis, not in a paper. But it's probably been thrown around since before, because it's a very natural question. It's almost unthinkable that no one asked this question. Because, I mean, the Calkin algebra has been studied for arbitrary Banach spaces since the 50s, and there are a few papers on this. So let's look very quickly at some examples before we start going into a bit more detail. So the very first explicit Calkin algebra is for the Arguros Hayden space, where it is one-dimensional. And for us in this lecture, the field is the complex numbers. It doesn't really matter. Everything would work for the real numbers as well. I'm just singling it out because, I don't know, people in operator algebras and operator theory usually use the complex numbers. So this space has the scalar plus compact property. So if you model the compact operators, you just get a one-dimensional object. Another one that came soon after was a little L1 space with a convolution operation. So little L1 of n0, the positive integers or the non-negative integers. A little bit more about these two things later. And another recent example was for every countable compact metric space, if you look at the continuous functions on that, then this can be captured as a Calkin algebra. And this result is very similar to what I'm talking about today, but the proof is very different. And I will go into this very briefly, why this is different and why what was done there does not work now. So here's today's result. For every compact metric space, you can find the Banach space whose Kalkin algebra is C of k. And a couple of comments. Firstly, is that this identification here is isometric. It is possible to do it isometrically by some renorming in the end. So there exists a Banach space XC of k, so that the Kalkin algebra is homomorphically isometric to C of k. And some examples of such C of k spaces are C01, continuous functions on the unit interval, continuous functions on the Cantor set, continuous functions on the Taurus. All of these three occur as Kalkin algebras. And by Milutin's theorem, these are, of course, the same as Banach spaces. They are isomorphic to one another as Banach spaces, but they are not isomorphic to one another as Banach algebras. They look different. Okay, so this is the result. So how do we get there? So it is very important if you are interested in starting with a Banach algebra B, and you want to describe it as a Kalkin algebra, if you're interested in doing that, it is very important to understand the connection between quotients of an L of X space and a very tight control of the operators on the space X. So this also touches on modern Banach spaces or non-classical Banach spaces. So the very first important thing to understand is the space of Gauss-Marie, which appeared in 1993, or at least it was published in 1993, it's a couple of years older. And they solved the unconditional basic sequence problem. So they defined a space that doesn't contain any unconditional basic sequence inside it. And it had the additional property, which is interesting in our context, is that any operator on this space, let's call it XGM, can be written as a sum of a multiple of the identity. So we call this a scalar operator plus a strictly singular operator. And we imagine strictly singular operators as being very small operators. So in this sense, the operators on this space, they are all scalar multiples of the identity plus something very tiny. Something that we can perceive as an error or as noise. So this is indeed an extremely tight control of the space of bounded linear operators. And the result that this has is that if you take this quotient, all the bounded linear operators or the strictly singular operators, what you're doing is that for every operator, you're forgetting this S. You're just erasing it, striking it out. And if you do that, all that remains is the scalar. That's the only thing to account for. So this is why this quotient here is one-dimensional. So it's a one-dimensional Banach algebra. And this was the first step towards understanding quotient algebras, at least in this context of L of X spaces and the tight control of operators on such spaces. So if you understand the format, the form of an operator on the space modulo something small, then you also have a similar understanding of the quotient over the small. And not the next step, but the thing that I want to present next is the Arguros Hayden space. So they did Arguros and Hayden did something even more strict, even tighter control of operators on the space. So they defined the Arguros Hayden space. It appeared in 2011. It was published in 2011, in which they solved the scalar plus compact problem. They defined a space on which every bounded linear operator is a sum of a scalar operator plus a compact operator. And what this means, if you take the space of all bounded linear operators and you quotient out the space of compact operators, then you're always striking out, erasing this compact operator. So again, you're left with a scalar here. And therefore, the Kalkin algebra of this space is one-dimensional. So a couple of things to say on this. So the Gauss-Marie space, this is defined as a combination of taking Schlumpf space and a Moret-Rosenthal space, a coding function that they used. And the Arguros Hayden space is defined by taking the Gauss-Marie space and maybe changing it a little bit. Instead of using Schlumpf space, you use a mixed zero setting, which is some type of discretization of Schlumpf space, which just makes calculation a bit easier. And then you have to combine it with the Burgen-Delbene construction. So you take everything that was known about modern Banach space construction back then, and you have to put them all together. And this is what gives you the Arguros Hayden space. And something that we learned from this comparison, and it has been used in a couple of instances since then, and this is also what today's lecture is based on, or at least this is the message, one of the messages I'm trying to convey, is that if you are able to exhibit a certain phenomenon on a space of operators, modulo strictly singular operators, in particular in a Gauss-Marie space. So if you're able to do something modulo strictly singular operators in a Gauss-Marie space, then it is highly likely that you will be able to exhibit the same phenomenon modulo compact operators on an Arguros Hayden space. So this is, of course, this is not always true. This is not a theorem, but it is an intuition. These two objects, the Gauss-Marie space and the Arguros Hayden space, are in certain ways compatible. And if you're able to do something here, you have a good chance of being able to transfer it here as well. And I want to talk about this more specifically now. Okay, so these were the first two very, very specific examples of tight control of operators. The only operators were scalar operators modulo some very small ideal, either strictly singular operators in the Gauss-Marie space or the compact operators on the Arguros Hayden space. So what Gauss and Moret tried to do soon after their first paper, a few years after the first paper, okay, we know how to have a space where the operators are basically all scalar operators modulo those pesky strictly singular operators. Instead of having just scalar operators, can I introduce some other prescribed structure of operators? So I don't want them to be scalar. I want them to be something else, something specific. I decide what I want them to be. Can I achieve this? And they were able to come with a few examples by using as a launching pad their original Gauss-Moret space. And among other such examples, they were able to define a space. Let's denote it XGM uppercase little l1. So it's a space with a Schauder basis with the following property. On this space, you don't only have scalar operators, you have more things. In particular, on this space with a basis, the left shift and the right shift are bounded. Okay, so these are definitely not scalar operators. And if you have a basis, you can shift to the left, shift to the right. But not only are these operators bounded, they, together with the identity, are able to capture all bounded linear operators in a certain sense. So what they were able to achieve in this space is that if you take any bounded linear operator, then it can be written as a scalar operator plus a series of scalar coefficients with powers, positive integer powers of the left shift plus a series of scalar coefficients with positive integer powers of the right shift plus a strictly singular operator. And this was even done in such a particular way so that the coefficients in both of these series are absolutely summable. So what you do this way is if you erase the strictly singular operator, if you mod out the strictly singular operators, what you capture is, okay, this scalar and these two summable series of scalars. So what you get if you mod out the strictly singular operators is an L1 space. Okay, and you have somewhere the positive integers, you have somewhere the negative integers. Here you have 0, so this is why you get L1 over Z, and you also get a very particular Banach algebra structure, a very particular multiplication, which you can understand because you know what happens when you shift to the right a few times and then you shift back to the left a few times again. You understand this operation, so you get a very understandable structure in this Banach algebra, and this also. So this is what we call the convolution algebra of L1 on Z, and this also has another name. It's called the Wiener algebra, which is a space of functions on the disk, of complex functions on the unit disk, where you can look at those that have summable Fourier coefficients, and then it happens that the algebraic structure is the same. So I see there's a question, are there infinite dimensional Banach spaces X or the quotient L of X by N of X? Well, this is not known. As far as I know, this is not known yet. I have never thought about this, but I remember this question being tossed around in the past. So when you say N of X, I suppose you mean the nuclear operators. I don't think this is known. Or well, I'm almost certain this isn't known, unless someone solved it recently and just haven't published it yet. But this is a nice question. So open problem, big open problem.
What is the multiplication on this one, the Wiener algebra?
Okay, so here, so you have L1 of Z, so you have the unit vector basis. Let me switch to red because I just like. So this is the unit vector basis. And then at least on the basis, the multiplication is En times Em is En plus M. So E0 is the unit element. And the identity corresponds to E0 and the left shift or corresponds to E-1, the right shift corresponds to E1. And okay, so if you look at this in the Banach space, then when you shift left and right, you always sometimes kill an initial part of your basis, but it doesn't matter because you mod it out in the end. Okay, so this is the first interesting step, or one of the first interesting steps of introducing a prescribed structure of bounded linear operators on a space, and then relating this to a quotient algebra. So this quotient algebra is a very algebraic object, but if you want to understand this, you have to understand the analysis on your Banach space X. You have to make it in such a way so that you understand the operators on it, and then if you understand them well, you will also understand this quotient. At least in the Gauss-Marie setting, you can quotient out strictly singular operators. Not always, but this is the general intuition. This is how things should be thought of. Okay, so as I said earlier, if you can do something modulo strictly singular operators in a Gauss-Marie type space, which this here certainly is, then you have a good chance of translating this to a result in modulo compact operators in Arguros Hayden type space. And this is what Taurus did in 2013. So defined a Banach space, let's call it XT, on which Banach space, so this space has a basis, and this is modeled after the Arguros Hayden space on which there exist only scalar operators and compact operators, nothing else. On this space, there additionally exists a right shift operator. It's not exactly a right shift, but it looks like a right shift. It's very similar to a right shift. It's basically take a bunch of right shifts on finite dimensional spaces and string them together. This is more or less what it is, kind of. And the property of this space is that if you take any bounded linear operator on the space, then it can be written as a scalar operator plus a series where you have scalar coefficients with powers of the right shift plus a compact operator. And more so, the series is absolutely summable. And then if you quotient out the compact operators on the space, all that remains is this scalar here and this summable series of scalars here, where this means that you again get an L1 space, but this time you don't get the negative integers because you're missing the left shift operator. So in particular, the Kalkin algebra is this convolution algebra on N0, which is the integers together with 0. And this is the same multiplication as before, you just never go back. You can only go forward, basically. Maybe a couple of comments. One thing is that the previous L1 of 0, it looked like the Wiener algebra. This one, so it was actually the Wiener algebra exactly as the Banach algebra. This one, I don't know if there is a name for this Banach algebra here, but it kind of looks like the disk algebra, which is all. So I think it's a sub algebra of a C-star algebra where you just have only positive Fourier coefficients, the coefficients for positive integers. It looks like that. I don't know if this has a name. If this has a name, then please let me know because I don't know what this is called. So the other comment I wanted to make is that here you don't have a left shift operator, and this is not by omission. It's just not that Taurus was lazy and he didn't check whether he could do it for a left shift operator. It's truly a restriction of the Arguros Hayden construction that if you want, or actually the Bourgain-Delbine space, that if you want to introduce shift operators, certain right shift operators appear there a priori. You can find them, not specifically in the Arguros Hayden space, but in general Bourgain-Delbine constructions. You can find right shift operators in it already, but finding left shift operators is a bit trickier. So I really, at this point, I don't know if one can do this. I'm not saying yes or no, but it's not obvious. So he did not do L1 of Z. There's a 1 missing here. There should be a 1 here. He did L1 of M0. Okay, so here is a general guide on defining explicit algebras. You can do it yourself at home. It is a 3-step process. So start with an explicit Kalkin algebra B. take whichever you want, one that you like, and then you would like to represent it as a Calkin algebra of some Banach space. How would I go about doing this? L1 of 0 isn't isomorphic. No. Yes, you're right. L1 of 0 is not isomorphic to subalgebra algebra. Absolutely not. But it is similar to the disk algebra, which is isomorphic to subalgebra algebra, if I'm not mistaken. So it is algebraically similar to the disk algebra, or at least what I understand as a disk algebra. I'm not sure if these terms are universal. So this is what I was trying to say. Maybe I didn't say it right. Okay, so back to what I was saying. So here's your 3-step process on defining B as a Calkin algebra. First thing that you need to do is identify a class of operators on some classical Banach space, let's call it X0, which class of operators generates your desired Banach algebra B. For example, if you want to generate L1 of Z, then if your Banach algebra is L1 of Z, then take the left and right shift on acting on L1 of Z. Then inside the space of operators of L1 of Z, L and R generate, together with their powers, generate L1 of Z as a Banach algebra. Of course, I'm not saying that this is possible for any B. So this is like a general idea of how things should work. This is the first step. Take your algebra, your Banach algebra, and describe it as a space of operators, not necessarily on a Hilbert space, on some classical space that you understand, something with a basis preferably. You want to understand how it works on the basis. Second step, take a Gauss-Marie space whose quotient over the strictly singular operator looks like B. So what you want to do is take a space X of the type of Gauss-Marie where every operator can be written as something in C, or a linear combination of things in C plus identity operator plus a strictly singular operator. So you want to try to do that. Try to do what Gauss-Marie did. So learn that paper very well and try to transfer their methods. Of course, it doesn't work for any B, but this is what you try to do. And the third step is, after you have learned how to do this on a Gauss-Marie space, then try to transfer this, because intuitively these are compatible methods, transfer it to an Arguros Hayden space, where whatever you did modulo strictly singular operators is going to work modulo compact operators of this Arguros Hayden space, and then your Calkin algebra is going to be B. So this is the general recipe. Of course, this isn't going to work all the time, but this is a general method of approach. And the previous example that I mentioned, it is based on this approach, but there are other examples that are not based on this approach, and let me briefly mention them. So the first one worth mentioning is something that Niels and Tomek observed in 2017, namely that if you take finitely many copies of an Arguros Hayden space and you choose them very carefully, you want some of them to be repeated, some of them to be very comparable to one another in a certain sense, then you can create any finite direct sum of matrix algebras. And then this, by Artin's theorem, is all finite dimensional complex semi-simple algebras.
Pavlos, in that recipe, what's the role of X0, the classical Banach space?
The role is that you have an understanding of how these operators act, and by knowing how they act, you know how to compute their norm. And then when you do this exotic Gauss-Marie translation, you have an idea of what to preserve if you want to get the norm of B in the end. So it is important to understand not only the algebraic structure, but the analytic structure. Does this answer the question?
I have also a question. Why do you want to go to 2 and you cannot go from 1 directly to 3, or is this only because it's easier?
This is how you learn how to do 3. You can try to do 3 right away, and if you can, be my guest. But this is how. This is, if you don't know how to do it, these are the 3 things to do in this sequence in hope to learn how to do the final one.
Okay, I see.
This is a DIY guide. This is what it is.
Okay.
Yes. So that this is what Chris wrote is a comment of the precise relation of L1 of N0 and the disk algebra, how they relate to L1 of 0 and the continuous functions on the torus. Yes. So that very well put, but I don't want to go back to that right now. So Okay, so I was saying, so what Niels and Tomek observed is that if you take carefully copies of the Arguros Hayden space, you can produce any finite dimensional complex semi-simple algebra. And so something that was done slightly earlier, but it is the exact same principle, is the result that I had with Puglisi and with Daniele Puglisi and Despina Zismopoulou, where for every countable compact space, you were able to create a C of K Kalkin algebra. And the way this worked is you took an infinite sequence of very incomparable Arguros Hayden spaces and you combine them in an Arguros Hayden way. And this way you were able to get a C of omega. So this is your simplest infinite compact metric space, Kalkin algebra. And then if you iterated this process in a transfinite induction, you were able to create any C of alpha for countable ordinal alpha, and then or countable compact metric spaces are of this form, basically. So this is how you got this. But in principle, it's the same. You just take your Arguros Hayden spaces the way you understand them, and then you fiddle with them a little bit, and then you are able to create something, some composite space and composite Arguros Hayden space that gives you some Kalkin algebra. So this is not the same three-step process that I described before. So sometimes you can circumvent it. So sometimes you can't go directly to three. It is possible in certain cases. So both of these are based on the same principle. This here has some additional analysis that you have to do because you take this infinite sum and then you have this transfinite recursion. So it's a bit more involved, but the idea is the same. And it is what I call for this lecture a composite Arguros Hayden space. It's a combination of Arguros Hayden spaces. And this is also why in this result here, it was not possible to break free from countable ordinal numbers because you were stuck in this iteration. And it's not possible to take, at least I don't know how to take an uncountable Arguros Hayden sum. If you know, then maybe you know how to do this iteration to get maybe a C of omega 1 Kalkin algebra, but I don't know how to do this. So with a similar process, you can define other Kalkin algebras. For example, there's this paper I have with Daniele and Daniele Puglisi and Andreas Tolias, where you get the James space or the second dual of James space, if you will, which is a quasi-reflexive space. You can get hereditarily decomposable spaces or Kalkin algebras. And even if you want, you can get all non-reflexive spaces with an unconditional basis. And here you're asking, okay, this is a good question. Do you here have an isometric homomorphism? I don't think so. The way it is defined, you should have these spaces acting on Rn with the infinity norm. This is how this. Okay. You're asking about this one. No, here the way we wrote it, we did not get isometry. Looking back to it, maybe with some work it could have been done by renorming, but I'm not sure. So this was not written isometrically. It was written 1 plus epsilon for every epsilon. This is how this was written. Okay, so lots of good questions. So this was 1 plus epsilon. Let me write it down. For any epsilon, you could do a different construction for any epsilon. The 1 plus epsilon was important to be able to continue the iteration. So you are able to do other examples by taking composite Arguros Hayden spaces. So another example, maybe worth mentioning here, is in a paper of Skillicorn, where they observed that you can have a Kalkin algebra where the multiplication is trivial, but this means that it has an identity, it has a unit, and then all other elements which are away from the unit, if you multiply them, you just get 0, basically. But the norm there was not explicitly understood, so this is not exactly an explicit Kalkin algebra. Okay, so now I want to talk about the idea of proof. And I think that there is enough time. So what we want to do is go through the 3 steps in the DIY guide of how to define Kalkin algebras. When you construct an HI space, that's a good question. So I can briefly go back to this. So you have a space with a basis, which is an HI. So this is an HI space. Actually, it's the very same HI space that was defined by Tolias and Deliani and Arguros in a certain paper. And this is an HI Banach algebra. And it is a basis which kind of looks like the different spaces of James space, kind of. And it's the pointless multiplication there. So this is the multiplication you get. And the way this is defined is you take a space that has an infinite dimensional shadow decomposition. So it has this infinite dimensional projections. And these are the images of the bases in the Kalkin algebra. This is how this works. But okay, I mean, there are a lot of details going on there, but roughly speaking, this is how this works. You have a basis, which kind of looks like the difference basis of James space, which means all the partial sums are bounded. And there you have a point Gauss product. So if you look up the HI space of Arguros, Veligiani, and Toyas, it is that space. It is a Banach algebra, an HI Banach algebra, one that was already known to exist. Okay, so I want to go through the idea of this proof. Okay, so 3 steps. We start with the Banach algebra B, and in this case, it's a C of K space. For a countable, not countable, sorry, for any compact metric space, you call this B, and then you want to represent it as a Kalkin algebra. So the very first thing that you want to do is find a classical Banach space and a class of operators that you understand well, preferably that you understand well, right? Because you want to understand its analytic structure and how it acts on vectors. You want to be able to compute the normal vectors. This is important. That generates the C of K Kalkin algebra. This is the first thing you want to do. And if you remember your graduate functional analysis course, maybe your second functional analysis course, is that if you take a Hilbert space, take little 2, and you take any normal operator on it, then the C-star algebra that it generates, the unital C-star algebra that it generates, it's the continuous functions on its spectrum. So what is the unital C-star algebra? You take T, you take all of its powers, you take its adjoint, you take all of its powers, and then you take all these possible products, and then you take the closed inner span of this. And this is the unital C-star algebra generated by a normal operator. And this is always the continuous functions on the spectrum of T0. So this is your starting point. This is a type of operator that I understand, or at least I can construct and understand, and it generates a C of K algebra. And you might think, but I don't only want to generate compact subsets of a complex plane. I also want to be able to capture other compact sets. You promised us all compact metric spaces, K, right? Yes, okay. So if you look at commutative star subalgebras of the continuous functions, continuous operators on the Hilbert space, these are always CFK space. Commutative C-star algebras are always CFK spaces. So you can find these. You can describe them explicitly. If you know what your K is, you can explicitly define a commutative collection of operators on a Hilbert space that define C of K as a C-star algebra. And I want to talk about a specific such example. So for the purpose of exposition, for the remainder of this lecture, let's focus on the torus. Our compact metric space is for now just torus. It doesn't matter. Nothing that I say here really matters that we're using the torus, but just to be in a more familiar environment. So I want to start with a Hilbert space and find a commutative collection of operators that generate the continuous functions of the torus as a C-star algebra, which is, of course, a particular type of Banach algebra. So what I want to first do is define a dense subset of the torus. And you can take any one you want. Let's take a specific one. Start with an irrational rotation. So here's your torus. Take an irrational angle alpha and call this here Z0. Now take all powers of Z0. And I think it's Kroneker's theorem that if you start with an irrational rotation, then these powers, they are dense in the torus. Doesn't have to be this one, just for the purpose of exposition. What you do next is you start with a continuous function on the torus, and you want to identify this with a certain operator acting on a Hilbert space. And the way I do this is I define a diagonal operator with respect to the basis. So for this phi, I define a diagonal operator that sends the nth basis element of the unit vector base of L2 to a multiple of itself that comes for the action of phi on this nth element of this dense set. Okay, so what I do here is I make an identification between the nth element of the unit vector basis of L2 with this nth element of my dense subset of the torus. I make this identification. I identify the natural numbers as an index of the base of the Hilbert space with this dense subset of the torus. And then I identify every continuous function on the torus with a continuous function or a bounded linear operator on the Hilbert space, which takes the nth element of the unit vector basis and sends it to a multiple of itself that comes from the action of phi on this element of the dense set that I identified with the nth element of the unit vector basis. Then, if you do this identification between continuous functions on the torus and bounded linear operators on the Hilbert space, this is a homomorphic isometry, and this is standard to check. So in this way, you have created, okay, a commutative star subalgebra of the bounded linear operators on the Hilbert space that exactly generates the continuous functions of the torus. And this is one that you understand explicitly. You understand all its members. You understand how to compute their norm. And on a Hilbert space, if you take a diagonal operator, its norm, and this is somewhat important, and I will say in a moment why, this is important, that its norm is the supremum of its diagonal entry. So it's the supremum of these numbers here, which is exactly the subnorm of phi because of density. Now, of course, you could say, but I understand the spectrum. Why do I have to look at the diagonal edges? Why do I have to do this analysis? Because if you do this analysis, you get in addition that this doesn't only work on the Hilbert space. You can do this for any space with an unconditional basis. So you can take the continuous functions on the torus and define a homomorphic isometry into the space of bounded linear operators into any space with a one unconditional basis. And this is kind of important. I don't want to get too much into this right now. It is because on the Gauss-Marie space, it does not behave like a Hilbert space. It behaves like L1 in a certain way. This is because it is based on Schlompert space, which is full of L1 vectors. So if you want to control the norm and what the norm of operators is on the space that you create in the second step, you don't want them to be on a Hilbert space, or at least it's more convenient to have them on another space. So this here, you don't need to do it on a Hilbert space. You can do it basically on any space with an unconditional basis. So what we just did is a very thorough analysis of step one. Okay, I want to identify a very understandable class of bounded linear operators on a classical space that generates the continuous functions, for example, on the torus. And we just did that. Of course, you don't know if this is going to work, but this is a class that you understand as well as possible. And the conclusion is that the class that we need to look at is specifically diagonal operators. We want to understand diagonal operators in a Gauss-Marie type space. Okay, so now that we did that, we want to talk about step two. And we want to define a Gauss-Marie type space so that if I look at all operators on it and I mod out strictly singular operators, what I get is these diagonal operators that generate the C of T Kalkin algebra. This is what I want to do. I want to have these operators. I want all operators to look something like this here, plus a strictly singular operator. This is what I want. And so this is the first step. You can define a Gauss-Marie type space, and it has a non-unconditional basis, En. And before I proceed, this is very important. When you want to talk about tight control of the structure of operators, you can never do this. Well, I mean, of course, it depends on what you mean. But in this context, unconditional basis introduces many operators, so you can't really have very tight control of operators. So you want it to be non-unconditional. You want your space to be full of non-unconditional. And it has the following properties. Firstly, if I start with any Lipschitz function, not every continuous Lipschitz, here you have to make some concessions. If you start with any Lipschitz function, so I add some additional properties to my function. If I take this phi hat, this specific diagonal operator that I defined before, so on this basis here, then it is bounded. Okay. So in a certain way, you could not hope all of them to be bounded because this kind of would mean that the basis is unconditional. I mean, it's not. But if you talk about Lipschitz functions, there's some additional structure here, then these always define bounded linear operators by the exact formula I defined earlier. The second thing is if I look at any Lipschitz function, okay, on the torus, and if I look at its hat, and I mod out the strictly singular operators from it, so this is what I'm doing, I'm just subtracting any strictly singular part that it may or may not have, then the norm of this is the subnorm of phi up to some constant. So I'm not talking about isometries now because the isometric result is a bit more technical, that's all. So let's just forget about isometries for now. So these phi hats, modulo strictly singular operators, their norm is the norm of phi. And it's important here to mod out the strictly singular operators because these phis here, their phi hats are always bounded, but the norm are not necessarily comparable. This here might be, the norm of this might be much larger than this. You have to mod out the strictly singular operators. So these are two things. So what you have achieved so far is you have kind of represented C of T, or at least the Lipschitz functions inside C of t, inside the quotient L of x over S of x. And the third thing that you have is that, in fact, any operator on this space can be, it's not exactly equal. If you want to have a neat statement, it is not equal, but it can be approximated by operators of the form phi hat plus S, where phi is a Lipschitz function and S is a strictly singular operator. So up to some small approximation, every operator is of this form. And what this means that if you then mod out the strictly singular operators, you would get at the first step maybe at least the Lipschitz functions on the torus, but by the Stone-Weierstrass theorem, the Lipschitz functions, they are separating dense subalgebra of the continuous function, so they are dense. So this then means that you also capture everything else. So what you were missing here in these approximations, it actually captures all the continuous functions. So it is possible to do this. And I would love to be able to tell you a few more things about this construction, because there is something different going on here. This is not just take the original Gauss-Marie idea of introducing bounded linear operators in a certain way. You have to do things a bit differently here. And I want to say why, which is, I think this is the most interesting, beyond the result, the most interesting contribution of this soon to come out paper is this additional idea on how to introduce bounded linear operators in a different way. Okay, so how do you define a Gauss-Marie space? So you need a norming set. So what is a norming set? So you take a subset of C00, this is what the norming set is, you call it say W, and it has a bunch of elements which you want to satisfy some properties. Let's not look at these right now, but let's just look at this one maybe. It is small, it's just the supernorm of these elements are at most one, and then you have some additional restrictions. And now using this W, you can define a norm on C00 via this formula. So you take every F in W, and then you take an X in C00, and then you can define this action by the usual inner product. And now this is a well-defined action, and no. So Chris asked if this particular dense subset special. No, it is not. It is not. It is of some importance in this example that if you throw out any finite subset, it's still dense, but you know, if you don't have isolated points, this is always the case. This is perhaps maybe the only detail you want, throwing finite away, finitely many things of the dense subset, you're still dense. That's the only thing you want. So it doesn't matter. I just wrote it down for expository purposes. So as I was saying, so you can take a subset of C00 if under some mild conditions here, it defines a norm on C00 via this action. So then this is called the norming set. And to define our space, this Gauss-Marie type space where the quotient over the strictly singular operators is C of k, we will define a specific such norming set. And I would love to be able to tell you a few things. Maybe I can take a few more minutes, and stop me if I go too far. So there are these parameters that you need to fix. If you're going into technicalities, these are important. You need to fix two very rapidly increasing sequences of natural numbers, mj and nj. And what you want is that each nj is much larger than 2 to the mj, basically. Or what is, if you want to look at this differently, is that basically 1 over mj is much smaller than 1 over log nj. So these are the mixed Tillotson parameters. And with these, you define a set, a norming set WCT, which satisfies among a couple of other Gauss-Marie-like properties. I want to focus on the ones that have to do with the boundedness of diagonal operators. So it has the following minimality condition. If you take any member F of this norming set, it has to be of two forms. Either it is a basis element. So I denote here the unit vector basis of C00 by EI star because I look at it as a sequence of functions. Either it is a basis element, maybe times a scalar or something, but just to simplify here. And if this is the case, by convention, I will say it has weight 0. This is of some importance. There are weights here which are actually quite important to this construction. So either it is of this form, or as in the Gauss-Marie type space, and as it happens in Schlumpert space, it has to be, if it's not a basis element, it has to be of the following form. There have to exist other members of the same norming set, which are successive in C00. So they are successive members of C00. Their supports are successive. That are for some J and J many of them. And F is the sum of these weighted by 1 over mj, where this mj and nj are connected. So remember, mj is in essence, or 1 over mj is much smaller than 1 divided by log nj. So there is this weighting. Okay, you take this nj many members of WCT that are already in there, you combine them, and then you weight them by this weight here, which is relatively small, or maybe not the better way to say it, that it's not too small compared to this number of members that you took. Now this year, you're still within the constraints of Schlumpert space or a mixed Shelson space. There is nothing really new going on here. There are two things that you need to do additionally. The first thing that you want to do is that the weights of these FIs, they are already defined, and I didn't say this, but if an F is of this form, then we'll call its weight to be this coefficient here. This is important. And if an F is of this form, then it has a weight, which is this number here. And if it's of this form, it has a weight that is 0. Now, if an F is of this form, it is absolutely required that these Fs have weights that go very fast down. And there are some ways to make this specific. They have to decrease very rapidly. And this is what is called a saturation under constraints of this set. And this is a technique that was initially used by Odell and Schlumpert when they found the space that had the whole interval 1 infinity as a Krivine set. And then in a series of papers by Arguros, myself, and there were other authors involved too, Beanland, Freeman, one paper with Denka. This technique has been used many times for many different things. But usually it was done with averages and not with weights. And with weights, it was first done in a recent paper in 2020 by myself and Arguros, where we found spaces with a unique spreading model and a non-unique asymptotic model. So it is crazy how versatile this tool is. It's been used for many different things. It was also used in the sense of averages to define the first reflexive space with invariant subspace property. So this has many applications. So you want this to decrease very rapidly. This is actually very important in this construction. I don't know a way to do it without this. And there also has to be a metric construction, a metric restriction. And it is the following. So if you have an F of this form, each of these FIs has a support inside M, and each of these supports, okay, has a bunch of N's, each of which was associated to a member of your dense subset of the torus. And so each FI comes together with a subset of the torus. And you demand that these subsets of the torus, they are very, very small, and they are very, very close to each other. This is what you demand. And of course, you have to make this precise. But you add this additional metric constraint on the members that you're allowed to take inside WCT. And these two are the most important thing. And if you have these two things together, this is the heuristic conclusion. This is what you're able to do. What this means in the end is that if you take any member of this norming set and you look at its support, up to some perturbation, you can get rid of some noise, and you are left with some F tilde, so that the diameter of the support of F tilde, if you look identified with the subset of the torus, this is tiny. So you have the torus here, then the support of F corresponds to some set here. This is the support of F. And if you get rid of some noise, which is small in a certain sense, then what you're left here is with a set of very small diameter, which is centered around some point ZF. So this relates to F, this ZF. And if you're able to do this, what happens next is that if you look at any Lipschitz function, I lost this picture, what a shame. If you look at any Lipschitz function on this very small set, the support of F tilde, because this is a set of very small diameter, it is basically a constant function on this set. So I have a constant function, and what this means is that F on this is basically equal to ZF. So F here is basically equal to F ZF. And now if I translate this to a multiplier acting on my space, when it acts on the support of this phi, this means that on it, it is basically constant. So this means that when I act this phi hat on this Z, I basically get a constant multiple of F. This is what happens, a scalar multiple of F. And this is basically the new idea. Every member of the norming set, if you act this prescribed diagonal operator, which is Lipschitz, so you want some tight control of its continuity, then it is basically a constant multiple of f. And it is kind of crucial that these scalar multiples here, for different f's, you get different scalar multiples. Otherwise, you would only get a constant function. You don't want it to be a constant function. And to make the statement more precise, so this is also how the weights come in. The statement is the following: if you start with any Lipschitz function on the torus, then depending on the Lipschitz plus the Lipschitz constant plus the sup norm of this phi, there exists some n. So that if you look at any f on the norming set that starts after n, it supports that after n, then this phi f is very close to a scalar multiple of f, and this very close depends on the weight of f. And the smaller the weight of f, the smaller this 1 over nj, the closer it is. For example, if the weight is 0, then these are equal. If the weight is not 0, but it is very small, these are very small. And of course, here I'm talking about phi in a dual sense. You're acting on the norming set, which is subset of the dual, but then you can pull this back to the space, and this tells you that this phi here is bounded. And then in the end, you can prove all these additional things. And as a final slide, there is this 3 steps process. There is a third step where all I said that you can do on a Gauss-Marie space, you can also do it on a Arguros Hayden space. And the way it is written here, you don't get an isometry, but then you're in normal, you can get an isometry in the end. So this is possible to do. A comment to be made, worth making at this point, is that you can have a Gauss-Marie space that satisfies that its Kalkin algebra is the continuous function of a compact metric space without going through this new Gauss-Marie type construction with the weight constraints and the metric constraints. But this does not work well with an Arguros Hayden construction. You have to do this new thing for it to work well with an Arguros Hayden construction. And it is, at least for me, it's kind of remarkable that you end up with a Arguros Hayden Burgendel-Pine space on which you have bounded diagonal operators. If you take the original Burgendel-Pine space, or if you take any Burgendel-Pine spaces that I'm aware of, they don't have non-trivial bounded diagonal operators. They have some bounded shift operators, but they don't have diagonal operators that are bounded. You have to do something different to achieve the bounds of diagonal operators. And basically what you do is that you have diagonal operators that on big pieces of the space are constant, but for different constants. This is what happens. When I say constant, I mean scalar. Okay, so I have 2 question slides. Maybe I can finish here. And maybe I can take your questions. If there is more time, I can go through these questions that I have written here. So I'll stop here. Thank you.
Okay, thank you so much, Pavlos. There was a lot to take in. I'm assuming there will be a lot of questions. So let's open for questions.
Is there just one problem on the slide?
No. I have more. There's 2 slides of problems.
Oh,
okay.
So
yeah. Why don't you show all then? Maybe I don't know.
Okay. So I saw someone raise the hand. I saw it was Bill, and I want to take Bill's question. Then maybe I can go through this.
No question.
Okay. All right. So then, okay. So things to talk about. So we can do separable Calkin algebras. I mean, you can conjure up operator algebras that generate non-separable C of K Calkin algebra. So, you know, any non-separable commutative sister algebra is still a C of K Calkin algebra. It's a continuous function and a set of characters. But this requires some new idea. Using the current understanding of the Arguros Hayden construction, you cannot go to the non-separable setting. Things one could try to do is define, for example, a non-separable Arguros Hayden space. And I know that, I don't know if they're here, but someone told me in the past that they knew how to do it. I don't know what happened with that. So that person, if you're here and you know how to do it, that would be a useful idea to have right now. And so there have been ideas to do non-separable Burgendel-Bind spaces based on the Burgen-PCA construction and a paper by Jordi Lopez-Apad. But I don't know how this translates to the Arguros Hayden setting. So as far as general non-separable C of K space Calkin algebras go, Benz and Tomek proved recently by some pigeonhole principle, combinatorial pigeonhole principle, that you can find C of K spaces of large density, continuum, or even basically any density you want, that are not Kalkin algebras of some space of the appropriate density. So this does not mean they are not Kalkin algebras, but it means they are not Kalkin algebras of a space that is of similar density. So this is the first result that I know of some restriction of whether a Banach algebra, unital Banach algebra, can be a Kalkin algebra even of a certain type. And I know that Tomek is very interested in this question in general. Are there any conditions that you can impose on a Banach algebra that completely preclude it from being a Kalkin algebra? There should be something, like intuitively, is it possible that any Banach algebra is a Kalkin algebra? Probably not. But what are the conditions that don't allow a Banach algebra to be a Kalkin algebra? We don't know. So this would be very interesting to have some understanding of this. From a Banach space point of view, it is very interesting to ask if there are reflexive Kalkin algebras, because a space with a reflexive Kalkin algebra would have to be a very funny space. For example, there are quasi-reflexive Kalkin algebras, I already mentioned it, but the spaces that are used to define quasi-reflexive algebras couldn't possibly give you reflexive Kalkin algebras. This is worlds apart from having a reflexive Kalkin algebra, so they have to be different. Yes, thank you. Reflexive and infinite dimensional, of course. Reflexive and finite dimensional, we know. So in the forthcoming paper, there is like some comment. It has to do with infinite dimensional shadow decompositions. A space with a reflexive Kalkin algebra cannot have an infinite dimensional shadow decomposition, for example. And the second slide of question is a discussion I've had over a couple of emails with Chris Phillips. And okay, so all these examples I mentioned are in essence commutative. They're not all commutative. There are these matrix algebras, and you can have similar like arguments that give other types of matrix algebras and sums thereof. And I don't know if there is a name of Banach algebras that you can obtain by performing elementary operations on commutative Kalkin algebras. If there is, I would be very interested in knowing it. But can you create Kalkin algebras that are truly non-commutative? And he said, start with the following non-commutative sister algebras. For example, the universally hyperfinite algebra of type 2 to infinity. This is defined by taking a certain type of embeddings of matrix algebras into one another and taking a limit. Or the Kunz algebra. So Gauss-Marie did something similar to the Kunz algebra. So there is some hints in their paper as to how to start on this, but you know there is a big gap between what they did and a Kunz Kalkin algebra, but they have the starting point there. And according to Chris, the particularly nasty reduced sister algebra on the free group of two generators. I'm not entirely sure why he calls it particularly nasty, because these two here as spaces of operators, you can understand them as you know, as an analytic object, whereas this here as an analytic object is a bit less, you know, nice to write down. You have to be a bit more artificial. This is easier to understand as an algebraic object. As an analytic object, these two are a bit nicer.
All of them have easily described specific representations on little L2 of something, even the UHS algebra.
Yes, I agree. So in our conversation, you didn't tell me, I was able to find it. But of course, if one sits down and thinks about it,
it didn't occur to me but until listening to your talk now.
Yes, you can write it down. I agree. I know how to write this down. But the things that you write down for these two are a bit simpler, at least how I thought of it. Here you have to do it, you know, it's like a page to describe. Okay, so that's all I had to say. I have the thank you slide, but maybe I want to leave
the reduced C-star algebra is nasty from a C-star algebra point of view, and in particular, it doesn't have the universal property that the full C-star algebra does, making it in various ways hard to work with. On the other hand, it does, unlike the full C-star algebra, have sort of Lipschitz-like dense subalgebras. Well, at least unlike in an obvious way for the full C-star algebra, there are Lipschitz-like dense subalgebras. And that's true of all of these things.
Yeah, okay. I have to say I'm not sufficiently familiar. I thought about these things a little bit, but more, you know, from an analytic perspective. The algebraic perspective, of course, is important because it comes into play when you want to when you want to understand, you have like your unit elements and you want to understand the products and how they behave. But I thought about it more from an analytic.
Yeah, if the Lipschitz part is key, then I think that can be done.
Okay. Yeah. So I invite everyone who is interested to try to follow the 3-step process and get to these 3 examples. And I have written some more comments on the.
Yeah. Okay, I do have to leave, unfortunately. So
thank you for coming.
excellent talk. Thank you.
Hi, Pavlos. So I want to second. This talk was excellent. So let's say you have 2 Banach algebras which you can represent as Kalkin algebras. Is it possible to establish that if you perform certain operations, some kind of maybe free products or whatever on those Banach algebras, the outcome will be once again representable as a Kalkin algebra?
Oh, not that I know of. I wouldn't say that this is an easy thing to do, because you have to probably start use, it's a Kalkin algebra of an x1, then a Kalkin algebra of x2, and then you want to combine x1 and x2 in a certain way, and this would depend on the type of operation that you take between the Banach algebras, right? And then depending on this type of operation, you would like to have some sort of understanding of how operators from x1 to x2 behave, because when you mix these things, then you have operators going from x1 to x2, right? And so then maybe you also want to be able to understand how these x1 and x2 behave with respect to one another. And if you have this understanding, then maybe you can do some of these things. But this is crucial to have as well, and understanding how these underlying Banach spaces x1 and x2 behave with one another. So starting with the Banach spaces x1, x2 alone, it does not allow you to combine them very well, because you don't know how you go from x1 to x2.
Thank you very much. I unfortunately have to leave.
Thank you for
Thank you again for a very nice talk.
Thank you.
Niels?
You're muted.
He's not muted, but I think his microphone is maybe not.
Oh, his microphone doesn't work.
Yeah.
Let's try without it. Can you hear me now?
Yes.
Okay, better, good. Okay, I'll take this one off then. So thank you for a very nice talk. So what I wanted to say is my sort of favorite example of things that shouldn't be a Kalkin algebra would be something like L of x for an infinite dimensional Banach space. And if you wanted to stay separable, you could, for example, take the Arguros Hayden space and look at L of it, right? Could you imagine that would be a Kalkin algebra? Would your methods give you any hints about that?
I think you should start with a UHF algebra, and then if you can do that, maybe you can go further, because this is, it is this combinations of matrix algebras, and if you can do that, where your pieces are all very well understood, if you can do that, then maybe you can extend to operators which are not restricted to finite dimensional pieces. So we're far away from that, but I think this is where to start with a UHF algebra.
Okay, thank you.
Okay, no more, I suppose. Thanks so much, Pavlos. That was a very impressive talk. So let me stop recording.